So in this video, I'm going to discuss about mathematical expressions, important mathematical expressions in series RLC resonant circuit. So here, circuit resistance, inductance, and capacitance are connected in series, and that combination is connected to a voltage source. There is a current in the circuit, and the circuit is said to be resonance when XL equal to XC. So here these are some mathematical expressions. So series RLC circuit. So first mathematical important mathematical equation is condition for resonance. When can we say the series RLC circuit is under resonance? Means when a reactance offered by the inductor equal to reactance offered by the capacitor, then we can say the series RLC circuit is under resonance. So XL equal to XC. XL is reactance offered by the inductor and XC is reactance offered by the capacitor. So under series resonance, so if we draw the diagram of current in the circuit against frequency, so current curves looks like this. So this is the current curve, means as you go on increasing the frequency, current in the circuit RLC circuit increases and goes to the maximum, and again it decreases. So at which frequency current in the circuit is maximum, that frequency is said to be a resonance frequency, and 1 by root 2 times of the maximum current. So here Im is the maximum current, in that 1 by root 2 means 71% of the maximum current in terms of percentages is Im by root 2. So the corresponding frequencies of Im by root 2 are lower cutoff frequency and higher cutoff frequency. So together called as a cutoff frequencies. So how do you get the cutoff frequencies? So we have to first get maximum current in the circuit. So maximum current in the circuit we get at resonance frequency. So in that maximum current we have to take 1 by root 2 times of the maximum current, or Im by root 2. Now we have to draw a dotted line at Im by root 2. So it cuts, definitely it cuts the current curve at 2 points. So if you project that related points onto the frequency axis, we get F1 and F2. F1 is called as lower cutoff frequency and F2 is called as higher cutoff frequency. So at the cutoff frequencies, current in the circuit is Im by root 2, or 1 by root 2 times of the current at resonance. Difference of this lower cutoff frequency and upper cutoff frequency are called as a bandwidth. Now we have to get mathematical expressions for this F1, F2 and bandwidth. So that are, so resonance frequency. So resonance frequency mathematical equation is F naught, or otherwise Fr equal to 1 by 2 by root LC hertz. So in terms of hertz, so this is the resonance frequency. So in terms of radians per second, omega naught, or otherwise omega r equal to 1 by root LC radians per second. So next is lower cutoff frequency and upper cutoff frequency. So lower cutoff frequency mathematical expression in terms of radians per second is omega 1 equal to minus r by 2l plus root r by 2l whole square plus 1 by LC. So it is in radians per second. So even we can find this lower cutoff frequency if you know resonance frequency and bandwidth. So resonance frequency minus 1 by 2 of bandwidth is also the lower cutoff frequency. So similarly higher cutoff frequency. So higher cutoff frequency mathematical expression is omega 2 equal to r by 2l plus root r by 2l whole square plus 1 by LC. So if you know resonance frequency omega naught and bandwidth, so higher cutoff frequency equal to omega naught plus bandwidth by 2. So similarly, so two more important frequencies are, so here if you see this diagram, here voltages against frequency, we have voltage curves against frequency. So this is VL is the voltage across the inductor against frequency. So VC is the voltage curve across the capacitor against frequency. So if you observe the voltage across the inductor curve against frequency, it increases to a maximum value and then decreases. So at which frequency voltage across the inductor is maximum, that is FL. So similarly, if you observe the voltage across the capacitor waveform, so voltage across the capacitor increases to a maximum value and then decreases. So at which frequency voltage across the capacitor is maximum? So that frequency is Fc. So here we have to get mathematical expressions for these two frequencies, FL and Fc. So frequency at which maximum voltage occurs across the capacitance is omega c. Let it be omega c in radians per second, which is equals to root 1 by LC minus r square by 2L square radians per second. So similarly, frequency at which maximum voltage occurs across the inductance. So omega L in radians per second, omega L is 1 by root LC minus R square C square by 2. So all these mathematical expressions depends on the resistor, inductor and capacitor value. So if you observe here, condition for resonance XL equal to XC. So resonance frequency expression, so it depends on L and C value. So lower half power frequency depends on RLC value. Higher half power frequency depends on RLC value. And frequency at which maximum voltage occurs across the capacitance. If you know the values of RLC, we can get omega C. So similarly, frequency at which maximum voltage occurs across the inductance. If you know the values of RLC, we can find this. So here important frequencies in resonance is so in series resonance. So now we are focusing on the series RLC circuit. So series RLC circuit is resonance frequency, lower cutoff frequency, upper cutoff frequency and frequency at which the voltage across the capacitor is maximum, frequency at which the voltage across the inductor is maximum. So next is so here bandwidth. So bandwidth is equals to difference of the frequencies, cutoff frequencies. So omega 2 minus omega 1. Here frequencies are in radians per second. So omega 2 minus omega 1 radians per second is the bandwidth. So if you know RLC values, so at that time what is the bandwidth is R by L radians per second. So resonant frequency, if you know cutoff frequencies and at that time what is the resonance frequency? So omega naught equal to root omega 1 omega 2 radians per second is the resonance frequency when cutoff frequencies are given. So similarly, product of the cutoff frequencies. So omega 1 and omega 2 are the cutoff frequencies in radians per second. So what is that product? Equal to 1 by LC. So after that, important is quality factor. So quality factor, if you know the values of resonance frequency in radians per second, inductor and resonance value and resistance value, so quality factor of the circuit, series RLC circuit at resonance is omega naught L by R. So similarly, if we know cutoff frequency, that is resonance frequency in radians per second, C value and R value, so at that time quality factor of series RLC circuit is 1 by omega naught CR. So if you know the values of RLC, so what is the quality factor of series RLC circuit is 1 by R root L by C. So similarly, if you know resonance frequency in radians per second and cutoff frequencies in radians per second, so at that time quality factor is equals to resonance frequency by bandwidth. So omega 2 minus omega 1 is called as bandwidth. So resonance frequency by bandwidth is also the quality factor. So next and last expression is selectivity. So selectivity is also equal to omega naught by difference of the cutoff frequencies. So omega naught is the resonance frequency and omega 2 is the higher cutoff frequency and omega 1 is the lower cutoff frequencies. So it is the ratio of resonance frequency to the bandwidth is selectivity. So these are the important expressions. So these are the important expressions for series RLC circuit. So if we are thorough with this mathematical expressions, we can solve any type of problem given in this series RLC resonant circuit.